We start off with a generalization of the directions we described for locating a point associated to an element in R2 or R3. So our first definition is a vector. A vector of dimension m is an m by 1 matrix. V for vector is equal to x1, x2, etc. down to xm, where each of the xi are just real numbers. We regard a vector as a set of instructions that tells us how to move through Rm from an initial position to a final position. As we saw in the last 3 examples, in Rm there are m orthogonal or perpendicular directions. So each number tells us how far to move in each of those directions. To get a feel for how this works, we're going to work in low dimension, where we can actually visualize, and then we will abstract to the higher dimensions. In one dimension, a vector, v, is a 1 by 1 matrix consisting of a single number, x. This is simply the data of a direction, which is encoded by the sign of x, and the magnitude, encoded by the absolute value of x. The direction tells us to move left if it's negative, or right if it's positive, while the magnitude tells us how far to move. For example, the vector v, given by the 1 by 1 matrix with a single entry of -2, tells us to move from our initial position 2 units to the left. It is important to note that the vector specifies how you move, but does not specify where you start. Generally, we represent a vector as an arrow. It has a tail at a starting point, and it has a head or a tip at an ending point. Different moves can be represented by what are called equivalent vectors, in the sense that the two vectors differ only by a translation in the ambient space. So here we can see that the vector v, if it is placed with its tail at the origin, points to -2. While if we place the tail at 2, the vector v will point to 0. These vectors are not equal because they're not literally the same, but they're equivalent because they basically give us the same data. Start somewhere, move 2 units to the left. For 2-dimensional vectors, we're going to envision a game. Stand in the center of a room. The point on the floor represents the origin of the plane. Look directly at one of the 4 walls. It doesn't matter which, just make sure that it's straight ahead in front of you. And we'll set the following orientation. The wall in front of you corresponds to the positive y direction. The wall behind you corresponds to the negative y. The wall to your left corresponds to the negative x direction. And finally, the wall to your right corresponds to the positive x direction. To move, you are only allowed to take steps in one of these 4 directions at a time. So, for example, you could take a step forward, you could take a step backwards, you could take a step to the left, or a step to the right. But you may not step diagonally. So let's consider a specific vector. The vector is v, which has its first entry 3 and its second entry 2. We can think of this vector as an instruction for the game. The first entry represents a move by 3 units parallel to the x-axis. That is, the first instruction is to take 3 steps to the right. The second entry represents a move by 2 units parallel to the y-axis. That is, 2 steps forward. As a whole, we think of the vector as an arrow, just like in the one-dimensional case, with its tail at your starting position and its head at your ending position. For example, if we were standing at the origin and we received this set of instructions for the game, then our vector v points from the origin to our final location, which is in Cartesian coordinates, the point 3, 2. If instead of starting from the origin, we had started from the point -3, -2, then our vector would point from that point -3, -2 back to the origin. Just like in the one-dimensional case, the two vectors themselves are equivalent. For three-dimensional vectors, we can actually extend our previous game. So if we imagine that we can also fly using the exact same orientation, standing in the middle of a room, thinking about the forward-facing wall as the positive y direction, the backwards wall as the negative x direction, left wall as the negative x direction, the right wall as the positive x direction. Our new direction is up towards the ceiling. That's going to be our positive z direction. And down through the floor is our negative z direction. So we could think about the vector v equals 1, 1, 1 as the set of instructions. Move by 1 unit parallel to the x-axis, or in our game, take 1 step to the right. Our second instruction is to move 1 unit parallel to the y-axis, or take 1 step forward. Our third instruction is to move 1 unit parallel to the z-axis, which in our game would correspond to flying 1 step up. Again, our vector points from the place we started to the place that we stop. We can visualize this arrow as the following. So the blue arrow points from the origin up to the point 1, 1, 1. If we drop a line directly from the tip of our arrow to the floor, that should be this red dotted line is 1 unit tall, and it should point to, in 3 dimensions, the point 1, 1, 0, which corresponds to the point on the floor that we think of as 1, 1 in R2. As a little remark about this identification that we just made, when we extended our game from 2 dimensions to 3 dimensions, we took our floor, the xy plane, and we threw in a 3rd dimension extending through our floor, going up and down. So we described R2 as a subspace of R3, something that we won't quite define just yet, but you should have an intuitive feel for what this means. We've identified R2 with the set of all points in R3 whose z-coordinate is 0. That's the set x, y, 0 inside of R3. So this allows us to view our 2-dimensional vector, say v equals 2, 3 from the previous example, naturally as the 3-dimensional vector, where our final instruction says not to move in the z direction whatsoever. So we can view this as a vector that lies totally within the xy plane in 3 space, i.e. the floor. So when m is bigger than 3, the vectors have the exact same meaning, but are difficult for us to visualize. It is therefore important for us to work examples in low dimension to gain intuition, then use our algebraic techniques to handle the details. So we're going to start by establishing the convention that unless specified otherwise, we assume that the tail of a vector is always at the origin. That is, the vector, whose coordinates are x1, x2, down to xm, is assumed to point from the origin, 0, 0, 0, to the point x1, x2, xm. Oftentimes, we will even go so far as to identify the vector v with the element of Rm to which it points, x1, x2, down to xm, and we'll even write the vector v as an element of Rm.